Hey guys, I hope it's going well. We're going to do lesson 5, which is trig identities. This is one of your first times you're going to work with proofs. And trig identities is probably the easiest one to work with when you're doing proofs. Not that it's easy, but it's also one of my favorite topics in math because it's like solving little puzzles. So I hope you enjoy it as well. So your goal when you are trying to show that you're basically trying to show two things are equal to each other. For example, I'm trying to show for this example that this side of the equation is equal to 1. And so for the layman, that's probably not obvious. And even for a mathematician, it's not completely obvious. So what we have to do is we have to show steps that prove that cos x tan x over sine x is in fact equal to 1. So in order to do that, we need tools in our toolbox that we can help to prove those things. So there's some steps to follow that are general things. Basically, with identities or proofs with trig identities, we're always trying to rewrite the equation so that it's in terms of sine and cosine. So like, for example, I want to get rid of this tan x. So what we need is something I can replace tan x with, which we'll see in a second. The other things that we're going to do are basically just algebra. So all of these things are just algebraic tricks. And the more you do these things, the better you're going to get at them. And so obviously we're going to practice a bunch when we do it. So here are our tools that we're going to use. And I'm actually going to prove these things, not that you would ever have to prove these things again. But one thing is that tan is in fact equal to sine divided by cos. And the proof for this, again, you're not going to have to show this ever, but if I take any triangle, right angle triangle, I call this theta. So this would be the opposite side, this would be the adjacent side, and this would be the hypotenuse. Well, sine over cos, if we think of it using those things, sine would be opposite over hypotenuse, cosine would be adjacent over hypotenuse, which in the end becomes O over H times H over A. So I flip the second fraction. So what happens is I end up with just opposite over adjacent, which is in fact tan. So basically this is the tangent identity, also called the quotient identity. And the second one here is the Pythagorean identity. You'll see in the actual formula, it looks similar to the Pythagorean theorem, only instead of sides, we get this. And I created another GIF because why not? And so in this one, if you follow along, what you end up with is things that represent sine and cos. So like x, remember x here, cos of theta is x over the radius. So if I square both of them, it's the same thing. And then in this one, it doesn't show it, but y over r is sine. And so if you want to, you can follow along, but you don't necessarily have to. So the next ones are the reciprocal trig identities, which we've seen before. And that's basically cosecant, secant, and cotangent. So cosecant is CSC, which matches up with sine, so it's 1 over sine. And secant is cosine. And then cotangent is actually the same as doing 1 over tangent, tan. But rather than writing that, it's best to write it in terms of cos and sine. So instead of 1 over tan, tan being sine over cos, I flip it. So it's cos over sine. And so in these cases, this is the same if I had sine theta is equal to 1 over cosecant, which you won't often use, but sometimes occasionally you would. And then secant is the same as cos being 1 over secant. And I had a little page, and maybe I'll attach it at the end of this video, but there are pages of these tools called trig identities that you would use in order to solve or prove things in trig. And when you get into university, if you continue in math, you'll get these sheets, and it becomes quite confusing and challenging, but always enjoyable to do. And so one thing with the Pythagorean identity, again, that's sine squared, cos squared equals 1. You can rearrange it, so you have sine squared theta equals 1 minus cos squared theta. And so that will pop up, and then you can rearrange it for cos squared theta, so it's 1 minus sine squared theta. They're the same formula, but they're good to see them in the different versions because it's easy to replace them. Okay, so let's actually try this out. So there are a couple rules. The main rule here is that when you're proving something, you cannot move things across the equal side. So we cannot move terms across the equal sign, ever. And so imagine this divide where the equals is. So the first thing I need to do is I need to rewrite it so I separate the two sides. So I say left side, or L dot S dot, equals cos tan over sine. And then I'm going to write it ridiculously far away just so we don't separate or we don't combine them. So I've got right side equals 1. So what you do is you choose one side to work with. You can work with both sides, but often it's easiest just to work with one. So you generally would choose the sign that has more terms in it or more things to work with. So when I look at this, obviously the left side is easier to work with. So I've got it written first. So what I need to do is I want to rewrite things in terms of sine or cosine. So tangent I can replace, which is sine x over cos x. And so because everything's written in x, I'm going to use x as the variable. So I've got cos x, so I replace it, sine x over cos x, and then all divided by sine x. And so after you replace something, generally what you do is you simplify. So your next step often after replacing would be to simplify it. So in this case, I've got cos and a divided by cos, so I end up with just sine over sine, which in fact is equal to 1. And so what we've done is shown that this is equal to the right side because the right side was 1. So therefore I'd state left side equals right side. And we're done. We've proven that original statement cos x tan x over sine x is in fact equal to 1 by using, in this case, just the quotient identity. Okay, next one a bit trickier. So again, we separate the two sides of the equation. So I say left side equals cos x, and then right side equals this thing. And if you want, you can try this out on your own. And this one's not too bad. So remember, we try to rewrite things in terms of sine and cos. So the first thing I can do is I can replace secant x with 1 over its reciprocal, which is cos x. And then obviously I'm going to replace tan with sine over cos, like that. So whenever you replace something, often you're going to simplify it. So I have 1 over cos x minus, and then I've got sine x times sine x. And remember, this is like having sine over 1. So the numerator times the numerator. So that becomes sine squared x. And remember, I write the squared before the x. And that's over cos. So at this stage, I've got the common denominator. And often in these questions, you'll notice if I look back to the left side, which is always good to do to look to the other side, I ultimately want to get to one term. At the moment, I've got 2 terms. So what I want to do is combine to make one term. And that's a general thing to help guide what you're doing. So in this case, I've got a common denominator, so I don't have to do anything to add them together. So I rewrite it so I've got one term. Now I say, okay, well, what next? And you always are looking for things that you might be able to replace. So this 1 minus sine squared, if I go back up here, 1 minus sine squared is cos squared theta, or cos squared x in this one. So this is my Pythagorean identity. So I can replace that simply with cos squared x over cos x. And now I've got something where I can divide a common factor. I've got cos squared, so the squared goes away and the cos x goes away. So I end up with just cos x. And if that isn't obvious to you, then just imagine this as being like, I don't know, y squared over y would simplify into y. That's basically what you have here. And so I've got cos x, and that obviously is equal to the left side, so therefore LS equals RS. And we've proven that identity. Just so you know, all of these identities will work. There is no trick April Fool's type thing that's going to mess with you in order to get it. Again, if you want to try this on your own, give it a shot. This one's got a bit of a trick to it. So I've start this out, left side equals, and separate and do the right side. So my left side obviously has more going on with it, so I'm going to work with that one. So notice the right side only has cos. There is no sine. So again, I look to the right side to give me a little hint. And the left side, what can I do with the sine squared x in order to make it into cos? What I can do with this is it is the Pythagorean identity. So I'm going to replace that with 1 minus cos squared x. And that's 1 over 1 minus cos x. Remember, in this case, some people would just want to cross out the 1s and cross out the square, but it doesn't work that way because this denominator has to be exactly the same as the numerator. So I can't do that. But what I can do is this 1 minus cos squared can be factored. This is like having a difference of squares. And it's not obvious, and this is the kind of trick to it. What you have is a perfect square of 1 minus another perfect square because it's cos squared x. So what I can do is separate that into 1 minus cos x over 1 minus or 1 plus cos x. And that's the difference of squares. And that's all over 1 minus cos x. And I'm going to write it in brackets just to accentuate what's going on. Now everything is factored. And we can simplify it. So I've got the same thing here and here. So this just becomes 1 plus cos x, which obviously is equal to the right side. So therefore, left side is equal to right side. And we're good. So a bit trickier, but not too bad. Next one definitely gets a bit more complex. But again, you can try it out if you want on your own. Okay, so I'll rewrite this. So I got left side, and we're going to need most of this space. And then my right side. This one, it's not entirely obvious what to start with, which side even. And in fact, this one is one of those cases where you possibly could work with each side separately. So we'll take a look at that as we go through. But I'm going to start, I think, with the left side. You could start with the right side if you want. But when I look at this, again, I'm starting with 2 terms on the left, or 2 fractions, whereas on the right, I've got 1 fraction. So ultimately, I know I need to combine what's on the left. Notice there is no squared, so I can't use Pythagorean identity. That doesn't work at the moment. But what I can do is create a common denominator to make them 1 fraction. So I'm going to create a common denominator. And you don't need to write this in if you don't want to, but just so you have some, makes sense when you look back on your notes. So if I write that in, that means I need to multiply each fraction by the opposite denominator. So this one I'm going to multiply by 1 plus sine x on the top and bottom. And this one I'm going to multiply by 1 minus sine x, top and bottom. So I do that, and I'm just going to move this down a little bit. So I end up with 1 plus sine x over 1 minus sine x times 1 plus sine x. Then I've got minus, and then it's 1 minus sine x. And the same thing in the denominator, 1 minus sine x, 1 plus sine x. And so now, notice I wrote the second fraction in brackets because I need to apply this negative to both terms. So I'm going to bring this all together so it's 1 fraction. So I'll rewrite it, 1 plus sine x, and then minus 1, and then plus sine x. And all of that over this 1 minus sine x times 1 plus sine x. So I can simplify the numerator, and also at this point, we can kind of look to the right side of the equation you notice that the right side has cos, so ultimately I'm going to have to make something into cos, but let's just simplify the numerator. So I have 1 minus 1, so that's gone, and then I have sine plus sine, so I end up with 2 sine x's. And then in the denominator, I've got 1 minus sine x times 1 plus sine x. So at this point, it's not obvious what to do, in my opinion, but what I can do is I'm going to go to the right side. So I'm just going to break this off. Because I have a tan x, I'm going to replace that. So let's see what happens when I do that. So I've got 2 times sine x cos x. And that's going to be divided by cos x. I'm going to write it this way because it's easier to work with. So I end up with 2 sine x over cos x. Doesn't matter where I put the 2, times 1 over cos x. So then I can simplify that. So I get 2 sine x over cos squared x, like that. So that helps a little bit. So again, I've still got one term on the right, one fraction. Notice my numerator is the same in both sides now, so that's good. What I can do with the denominator is I can refoil it. Because it's a difference of squares, and I'm kind of out of room, let me just back this up and I'll write it over here. I can rewrite this as 2 sine x, and then I'm going to FOIL the denominator because it's a difference of squares. So I end up with 1 minus sine squared x. Now what's going to happen? I try to recognize this, that's Pythag identity, and I can replace that thing with cos squared x. And if that is not obvious to you, I would not be surprised at all because you're just starting this. But you try to look for when you have squareds and 1, and often that's going to be Pythagorean identity. So now what I end up with is, and I'll just write this over here, that's equal to the right side, obviously, and therefore left side is right side. So you can see these are kind of like puzzles, but there's little tricks to get through them. And I think the more you do, the more enjoyable it gets because you start to figure it out. There are some challenging ones in the textbook to try. There are the questions. I've posted obviously the textbook there for those. I just want to add on this page here. This is an example of all of the trig identities that you might face when you continue on in math, especially if you go on in grade 12 math. So here is a couple of the ones we are using. So we've got these Pythagorean identities. Reciprocal identities, where are they? These guys, quotient identities or reciprocal. Then there is a whole bunch of other ones that you will learn at some point, but it gives you an indication of how many there can be. All right, just for perspective, it's good to see.